last talk of this session will be brought to you virtually, and it's going to be Susan Sheehan, and she's going to be talking to us about computational image analysis for aging mouse tissues.
Hi, my name is Susan Sheehan, and I'm here to talk about computational image analysis for aging mouse tissues. Our work builds on the geropathology grading platform that was first published by Snyder in 2019. This work generates a composite lesion score, allowing for the comparison between tissues from aging mice. However, there are some limitations to this platform, including moderate agreement between pathologists, it's time-consuming and has low throughput, and at the time of publication was only shown in males in 2 genetic backgrounds for 4 tissues. The work of the image analysis core at the Jackson Laboratory is to build upon this geropathology grading platform. Our pipeline is reproducible and high throughput and generates quantitative data that allows for comparison between 2 groups so we can tell if our interventions affect health span and lifespan, as well as generate data that's usable in genome-wide association studies so we can determine novel genetic drivers for image-related changes with age. Our pipeline, we want to be adaptable for many strains, both sexes, many tissues, and ideally many species. With the goal of quantifying aging in histological images in mind, we set out to use tools that utilize artificial intelligence and novel imaging formats to quantify aging in the context of images. Our goal was to seek out free open source solutions and link them together, adding value by providing directions and explanations that bring the world of computation, image analysis, and computer sciences to pathologists and research community at large. Many individuals in these communities may not have the experience or desire to learn coding language and may, for a variety of reasons, be hesitant to adopt some of these methodologies. I briefly want to talk you through some of the tools that we use in our final solutions, why they're important, and where you've likely seamlessly adapted them to your daily life already, as well as their application to medical imaging. The first thing I want to talk about is file format. This is important because of the advances in microscopes, which allow us to get whole slide scans at high resolution. Many of us along the way have taken an image similar to the example here, where we wanted to zoom in for more detail, only to find that it's become pixelated. Or we've tried to email a file to a friend or collaborator and get a mail or demon message. There are solutions to both of these problems by taking either a large number of higher resolution images or breaking up our data into multiple messages to email them, but neither of those are ideal. What we want is a solution that is small enough to share, but also allows for dynamic scaling. Something similar to what Google Maps does. Because I am a researcher in the United States at the Jackson Laboratory, I've shown my example here. You can actually zoom out and see the whole world, but here we can see the United States, and within the United States, we can zoom in and see Maine and also load neighborhood data so we can see where the Jackson Laboratory is in relation to downtown Bar Harbor. We don't load neighborhood data for the entire state or country and only load neighborhood data when we care about looking at things at that resolution. This is similar to what XAR file formats allow us to do with our whole slide images. We can look at them at low resolution and see where we are within the tissue. We can zoom in and see high level detail, and we know that this glomeruli is in this location in the overall tissue. However, as with many things, we don't want to become lost. Many of us have had the situation where our perspective in Google Maps has become disoriented and we don't understand where we are. We've also had the situation where people have left our research group and we have a large number of files that we can't make heads or tails of. Organization and metadata is not a very exciting thing, but it's very important, especially in context for images. with images, a way that organization metadata looks like in our daily lives is if you say you came to visit me in Bar Harbor and you are hungry, you might look up where are all of the restaurants in Bar Harbor. We can plot them on a map, and you might be interested in the one that's closest to you, or maybe you want a particular type of food, say pizza or lobster. Maybe you want to only see the restaurants that are currently open, or you want to zoom in on a particular restaurant and get information on its phone number, does it do takeout, what hours is it open or not? And all of this information is metadata to our image that we can get and search. Similar to that with our medical images, we utilize Omero, which is a open source offering from open microscopy environments that allows us to store our images by data set and project. And within those, we can have keywords and metadata as well as regions of interest. So here we can see the overall view of the whole slide scan, and we can zoom in at any given spot and actually look at what the slide looks like. We can see regions of interest, these red circles on this slide, and we can search for a variety of properties within either the region of interest or that apply to the whole slide in general. At this point, I want to start talking about some of the concepts of machine learning. And the first one is transfer learning. And this is a concept that is not specific to machine learning. It's actually how humans learn every day, and something that we as scientists do all the time. And this is the concept of taking something that we know and stretching it just a little bit to apply it to something that we don't know. It's how everybody learns data. It's how we do our data analysis and interpretation. In the context of machine learning and our Google Maps example, in the metropolitan cities, Google Maps on mobile devices now gives a parking estimate. So you can take your location and get directions, as you probably all already know how to do. And you also then get an estimate of what your parking availability is. This estimate is generated using transfer learning. It takes traffic data that it has from the GPS coordinates changing on our cell phones, as well as information about events in the area that you're going to, information from the Department of Transportation on construction. It monitors emergency channels to know about emergent situations, as well as takes into account published information on operating hours of parking garages, etc. In this case, you can also then move this little white ball back from your final destination. And maybe you can determine that parking is much easier 2 blocks away from your final destination. So instead of driving all the way into your final destination and then looking for parking in concentrically wider circles, maybe you drive only to 2 blocks to where your final destination is and look for parking in a place that is known to have a little bit better parking availability, and then walk in your final 2 blocks. With images, there are large data sets of images for all sorts of variety of daily life situations where cats and dogs and vehicles and flowers and fruit have all been identified. And what we want to do is take these collection of images and be able to then apply them to our medical images so that we can identify different tissues as well as structures within them. And that comes into the next concept, which is how are we going to identify them? What we want to do for this project is something called segmentation. So what we really want to do is not just say this image has a cat or a dog in it, but actually be able to tell where the cat or dog is. And we don't want to do that by object detection and just putting a box around it. What we really want to do is something called instant segmentation, where we can discern the 2 different dogs from each other. And importantly, we can detect subtle edge boundaries. For instance, this white cat is on a white pillow, and we can identify the specific edge of the cat, where the cat stops and where the pillow starts. We can use this segmentation in type of problem in our medical images to identify structures. In this case, all of the glomeruli identified by red blobs here on this H&E slide have been generated by a computer. And so you can actually put matrix on how exact you want your boundary to be, and you can set that beforehand and generate segmentations until they reach your prior approved threshold. And once we have, say, all of the glomeruli identified and segmented out of this tissue, we can then talk about putting scores specifically on the glomeruli as opposed to other structures within the kidney. Now we come to a portion of the machine learning talk that many people refer to as the black box. I don't like to refer to this part of machine learning as the black box. I like to think about it more as a Rosetta Stone. So we know what the pathologists see when they look at an image, and we know the vocabulary around that. This is fibrosis, this is inflammatory infiltrate, et cetera. So we have that vocabulary. We also know what the vocabulary is for the computer to see images, and that is a series of numbers and mathematical operations. What we don't have is the bridge that says that if a computer sees this pattern in the mathematical data that represents the image, it correlates to this vocabulary term that the pathologists use, and that's what we're building. What this looks like in practice is, in this particular instance that was published by our group in 2019, we looked at non-glomerular tissue between two different strains of mice. And we were able to give all of the non-glomerular tissues a machine score, a computer score in computer language. And then we just simply looked at the distribution of machine score for each of these images. And we can see that we can actually separate out the wild type and the knockout images based on machine score. When we go in and we look at examples of images that fall into the two extremes of these categories, we see that the more extreme wild type images all have denser tissue. They have more nuclei that are tightly packed and no real presence of vacuoles. The more extreme knockout animals have these vacuoles or holes in the tissues. The tissue itself is less dense. The nuclei don't stain as punctately, and there are fewer of them. And so this led us to believe that we had some sort of proximal tubule integrity issue going on, and we're able to then go in and validate this with immunohistochemistry, where we can see in the wild type animals, we have a nice intact proximal tubule brush border, but in the knockout examples, we have these this degradation and this hole and loss of integrity of the proximal tubule brush border, and we can actually quantify this. So our future plans are to link all of these tools together in a way that is easy to use with minimal coding, apply these tools and validate our tools using our mouse studies, as well as provide training and resources to the community. And specifically, if you're interested in that, please watch the American Aging Association YouTube channel, where we expect to be providing more in-depth explanation for all of these concepts, as well as step-by-step directions. Specifically, I'd like to thank the Shock Center at the Jackson Laboratory, specifically Ron, Gary, and Laura. At the other groups at the Jackson Laboratory are Computational Sciences, Matt Mahoney, Seamus Wave, and Mandy Chen, as well as the Research IT team, Dave and Eric specifically, as well as Jenna and Warren from the University of Washington. And I'd like to thank the National Institute of Aging as well. Thank you for your attention and have a great day.